I thought since many of you are staying here for quite a while, it's interesting to give a perspective on things and not so much on technical contents. So essentially, I was putting some basic information for you that you can find a lot of information on our webpage. So probably all of you know the NUHAG webpage. If not, go there. nuhag.eu is easily found. There you have a bar which says database and tools, and there are some subsections which are more interesting than others. One is the talk sections where you can find, I don't know, 1,000 talks of all the events that we have organized over the years, including all my talks that have been put in PDF format, so many of the PDF files. So when I was deciding kind of I just take one of them, I put a link to it. It's a talk which has been given in the first version a couple of years ago. So I feel a little bit ashamed that I'm giving the same story, but in many different variations already for many years. People still don't use the Banach Gelfand Triple, so I think it's worthwhile, or don't know about it. That's why I think it's worthwhile to tell you. So if you go there, you have the choice title. If you go title equals Banach Gelfand, then you find something like 10 talks with 7 of them, I think, with slides. One of them will be used today. Also, you find in our BibTeX section more or less all the papers on the subject. There are some MATLAB files, and I have done a course on applied harmonic analysis where some of the ideas went into this. So more or less for me, Fourier analysis is a branch of functional analysis. Whereas people in abstract functional analysis are saying, well, we work with Banach spaces. Well, when you do functional analysis with each Banach space, you look at the dual space. So Banach space is the dual space, all the operators. In harmonic analysis, we are interested in specific operators, the operators which commute with translations, the operators which are intertwining one group representation with another group representation. That's kind of how I worked with function spaces. I came from abstract harmonic analysis. I was doing a lot of abstract stuff for many years. Then I was thinking, well, one should do applications. Then I had a period where I was doing a lot of concrete applications in the more recent time with people from astronomy and so on, and irregular sampling stuff and so on. And nowadays, I'm promoting very much considerations, and it's running under I call it postmodern analysis, because my advisor was promoting modern analysis, so afterwards you do postmodern. But that's the question simply of what can you do with all the stuff that you have invented? So I would say in the early days of functional analysis, people were starting, okay, we have the Lebesgue spaces, the LP spaces, first L2, L1, L infinity, in between LP spaces. Some other people were generalizing to Lorentz spaces, Orlitz spaces, weighted spaces. Nowadays you have anisotropic Biesov spaces and all these spaces or so. So it's actually like in the real world. At the beginning you had some stuff in the market. Now you have the supermarket. You have 10,000 things. What are you needing? You need a consumer report, or you need people. Yeah, I think more and more in this way. You need people who are tell you, if you want to do this, try this space and this space. If you want to do this, try the other space. So a very interesting talk, which was actually in the priority program of Stefan Dahlke, was given by Joachim Buhmann from ETH Zurich. He was talking about the information content of algorithm. And he made a very nice comparison, which I repeat over and over again, which is, think of pharmaceutical industry. They are telling you the new recipe, the new mixture or so, is 20% more effective than the old one, which is very nice. So we're producing function spaces. We're saying we have a new function space. There's one more parameter, or the embedding is sharper, all these things. But then there are a lot of people who want to use these things. So these are the patients. They go to this doctor and say, well, I don't feel right, doctor. Can you help me? Can you tell me what I have? And once you tell me, which pharmacy would you recommend? And we really don't think about this. I mean, when you say, well, which function space should we use? Then if you start thinking about it, maybe you should use some function spaces which are compatible to what you want to do. The story of wavelet theory is very much a success story because Yves Meyer and the people doing Calderon-Sigmund operators were working very hard with what we call hard analysis methods to understand how to decompose functions into pieces and so on. And well, Calderon-Sigmund operators have to do with dilations. Therefore, it's not completely surprising, I mean, in retrospect, that function spaces built by translations and dilations, well known as wavelets, are really the good tool. So we find after many years that yes, it's plausible if you give me an orthonormal wavelet basis, actually a good orthonormal wavelet basis, which is not just a basis for L2, but which is a basis for Bezier spaces, then you can use it to represent the operator, which is a Calderon-Sigmund operator. It's nicely diagonal concentrated while decaying away from the diagonal. If you have theorems telling you that even the inverse of such an operator has the same property, then you can prove a lot of interesting theorems. Now, in one of my first meetings with Yves Meyer, I was quite excited about the event of wavelets, and I visited him in February, I think it was 88 or so, very early on, before it was, wavelets were a very big movement or so. And we had a relatively short conversation, but one sentence I remember very much was, well, function spaces are here for operators. And I'm saying, yes, this is his story. He had the operators, the Calderon-Sigmund operators, they discovered the Bezier spaces as appropriate tools, and then wavelets characterizing Bezier spaces, and everything was fitting together, and I was playing around with function spaces. I wanted to do smoothness spaces on locally compact abelian groups. There was no dilation, so I had to do something different. And so somehow, at some point, I realized it might be interesting to cut the function into equal pieces on the Fourier side. That's how modulation spaces appeared. Then I realized it has connections to the Heisenberg group. Then I had contacts with the engineers, and they told me, what you're doing is Gabbar analysis. Oh, what is Gabbar analysis? Well, this means you take a building block, you shift it around, and so on, and that story started. And later on, it turned out that, well, these function spaces are exactly the right function spaces for the discussion of slowly varying channels. So these were some of our projects on mobile communication. So I guess most of you have mobile phones, and what you receive from your base station is some signal. I don't like PDE, and certainly it would not be feasible to solve Maxwell equations saying we have a 3D model of the environment and see how the electromagnetic waves are propagated. But we all know that everything which is too far away is already decaying so much that it doesn't contribute. So there is multipath propagation between my mobile phone and the sending station. So things are coming up, but in a smeared way. We call it convolution. But and then if we sit here, or if my computer is connected to the printer, they're not moving. That's a convolution operator, so to say. The room gives you some convolution operator. But if I go around, or if I move in a car, in a high-speed train or so, there's even a little bit of a Doppler effect. Not just the ordinary Doppler effect of relative movement, but also the Doppler effect, I call it the implicit Doppler effect, that comes from a changing profile. Because if somebody tells you that he has an operator who is strictly a limit of linear combinations of translations, then you know it's a pure convolution operator. And the convolution operator is a moving average. So you have a profile, and that moves over the signal, and it's not changing. And the idea that we have now with slowly mobile channels is you have a convolution profile, but as you go, it's changing a little bit, not too much. If I go around the corner, I will receive not exactly the same combination of multipath propagation. So even if my speed is very low compared to electromagnetic propagation speed, I do not have an operator which has a constant profile. And if you have such an operator, you can build in MATLAB a matrix which has a convolution type shape along the diagonal. It's not constant, but there's a small change. Then you will find out that in its spreading representation, which I will discuss maybe later, you find out it's not purely translation. And so, well, suddenly it turned out modulation spaces are the right thing to work with this. Now, I've had the good luck of finding this Siegel algebra for Well, actually, the minimal Banach space, which is invariant on the time and frequency shifts. So you can also say it's the minimal translation invariant space, which is at the same time Fourier invariant, because you all know if you take the Fourier transform, shift the Fourier transform, and then take the inverse Fourier transform, you have done a modulation. So that's the same effect. And that's not only the prototype of all these modulation spaces, the modulation space with L1 condition, or you will see it in a moment, but it's also a very useful space for classical Fourier analysis. So my original motivation was to work on locally compact abelian groups. I saw Hans Reiter, usually I say, suffer from the Schwarz-Brouillard space, because it's really very hard work that you have to do, use structure theory, which he disliked, but he had to go through, because Schwarz-Brouillard has to be defined by using the structure theory for locally compact abelian groups. And so I thought it's even unfair. I mean, he was suggesting to work with wavelets. He was looking for a Siegel algebra with good properties. He didn't find it himself. He worked with Schwarz-Brouillard, and when I had the space, he was asking me questions, and I said, yes, I will look at this, and next day I came, yes, there's a half-page proof for what you want. So all the properties that he was needing for his work on metaplectic groups, following the ACTA paper of Andre Weil, can be done with the zero space. Franz Lueff is another very advocate of the space, because he was looking up a lot of work done in the theory of non-commutative geometry, which has very strong contributions by Mark Riefel. And Mark Riefel was using the Schwarz-Brouillard space because he wanted to do everything in the right generality. And Franz came along, and well, of course you have to do some hard work, but essentially said, well, with the zero space you have a larger domain and easier proofs and a better understanding. So, and finally I realized, even if you look at classical Fourier analysis, what is the problem there? You have Fourier transform of L1 functions. They may not be in L1. So what you do, you multiply them down to make them L1. So you use classical summability kernels. And nowadays we know that all the classical summability kernels are in the space S0. So actually I easily put up, I don't know, 50 euros if you find a good classical summability kernel which is not in S0. You have to be aware that you are fighting against Ferenc Weiss, who's really an expert. He spent 2 years with us, and he had 1 or 2 papers proving that all the ones that he knew are in the space. So somehow it seems to be that I would claim all these S0 functions are good functions for all kind of purposes, from time frequency analysis to classical Fourier analysis to stochastic processes to and so on. And you need arguments why certain kernels with certain good properties, especially Schwarz spaces, are in the space. Are in the space. Okay, so before going to the more technical details and descriptions, I also want to tell you. I mean, you all know the usual Gelfand Triple, which is the Schwarz space of rapidly decreasing function, which is very often used, of course, to say inside the Hilbert space you do nice things, and if you do PD, of course, you stay with this space and it's fine. If, however, and that's my clientele, so to say, you're working with electrical engineers or with people from abstract harmonic analysis, where differentiation doesn't play a role or even may not exist on an abstract locally compact abelian groups, you may look for replacements. Another thing that I would say is you can look at the thing also very often viewed as natural domain for maybe elliptic partial differential operators. You can have a Sobolev space of maybe S equals 1 of order 1, and you do a Laplace operator and you're mapping into this space, and you're using the fact that this operator is an isomorphism, and actually they're both Hilbert spaces. So in my terminology, one might call this situation a Hilbert space triple, and if you apply the Fourier transform to this, you would say, well, actually what he is doing is he is looking via Plancherel into into a setting where you have just weighted L2 spaces. And you make the weighted L2 space smaller by putting a positive growing weight. So I use this convention is 1 plus t squared to the power s over 2. So it's of growth order t to the s. And so clearly you have this situation. Now, so aside from the usefulness for partial differential equations, why would you use the Schwartz space also? That's a question now. If anybody has a suggestion. Pardon? Pardon for? Yeah, the Fourier operator, it's the space is Fourier invariant. And the usual trick is to say, well, if you have a tempered distribution, you can write the Fourier transform of the generalized function in a very natural way. So this is something that you cannot do here, but you can do it here. Now, I will show you a smaller space, and a smaller space which is, of course, also, not of course, which will be Fourier invariant as well. And then you have to be careful with your statement. So if you have an operator, the Fourier operator, which is mapping a small space into a small space and a big space into a big space, it sometimes sees statements that people say, well, we have a more general Fourier transform because we are having a larger domain. I'm saying, well, in many cases, you know that your object is in the small domain. And if the object is in the small domain and you have knowledge that it stays in the small domain after the Fourier transform, you have a stronger statement because the target space is smaller. So purely logically, if you have an operator defined on two domains, in very many situations, you cannot say one or the other statement is stronger. In one case, you can say the target space is smaller if you know a little bit more about the initial value. In the other case, you have a larger domain, but what you know at the end is much less, or is less. Okay, so I go directly, because I have the blackboard and we can do everything informal, to the situation that I would say a Banach Gelfand Triple is a situation like we have on the blackboard, that there is a Banach space sitting inside a Hilbert space, sitting inside the dual space. If you're familiar with complex interpolation theory, you might even say, well, it's enough to have a natural embedding of the Banach space into the dual space. Because if you then mix 50% of the dual space and 50% of the space, you get something which in all the cases I know, and I think one can prove it, is always a Hilbert space. But it's a little bit superficial because in our case, the embedding will be, of course, here is a space of test functions, and test functions should be just ordinary functions which are integrable and bounded. So if they're integrable and bounded, you can integrate one test function against another test function, and so in this way you're creating a functional. That's the usual way of taking a regular distribution, taking an ordinary function, turning it into a regular distribution. So the integration procedure, the existence of the higher integral, is allowing you, if these are test functions, to embed it in the dual space, assuming that test function space is not too big. I mean, if I take LP with P larger than 2, then even on the torus I have trouble and I cannot do anything. So that's why test function spaces should not be too big. On the other hand, if they are too small, it's nice because then the dual space is very big, but then we have other troubles. So I think it's a reasonable size test space is the right thing. And now if you look at the picture here, you see, so to say, the essence of what a Banach Gelfand Triple morphism is. So it's really, I'm talking a little bit now about category theory. We all know when you have mappings from groups to groups, they should be homomorphisms. From topological space to topological spaces, they should be just continuous. From Banach spaces to Banach spaces, they should be bounded linear operators. And now I'm creating or suggesting another category. So let's look at these triples. And what is the most natural situation? Of course, that each layer goes into each layer. So if you would look at the Fourier transforms just in the topological way, you would say, oh, it's good. We know Plancherel's theorem. We have a unitary mapping from the Hilbert space to L2. But if we restrict it to S, Schwarz space is invariant. Actually, you know that it's a continuous mapping, so you can estimate seminorms and so on. And by duality, it's also continuous. Well, continuous in which sense? What is the correct topology on S prime or so? And then I must say, I mean, of course, you have some idea and think of something like related or similar to weak star. Whenever you apply it, it's convergent or so. But there is no norm convergence here. Here you have norm convergence, but also because we have a dual space, weak star convergence. So that's already, in that sense, better. And it's interesting, I mean, because I'm interested to teach such things also to engineers, to look at the courses from that you can look up at YouTube, signal processing courses, for example, at MIT or Stanford. I found very amazing the course of Brad Osgood on the Fourier transform, how he's teaching engineers. He's saying, well, what is a tempo distribution? Well, you know, there is a complicated space with a lot of seminorms. We have no time to discuss it here. And when you have a linear functional, so linear measurements on this space, they have to be continuous. Well, what does it mean? It means that if a sequence phi n of test functions goes to a limit function phi 0, then it has to be respected by the functionals. The corresponding measurements are convergent in the complex numbers. Well, you know, but mathematicians spent 100 pages to describe what it means. Convergence here, we don't have to do this in all detail. Now, my viewpoint is, yes, if you work with topological vector spaces, you have to make a lot of effort. If you're in a Banach space, even engineering students would accept a continuous linear functional is a bounded linear functional, or it's an epsilon delta definition. So if this is smaller than delta, measured in the right way, so they don't have to learn, but they can even follow the argument. So if I have a Banach Gelfand triple, I would assume that all the three layers are norm continuous. And a kind of important trick is, because the dual spaces carry the weak star topology, in each case, I would like to assume that the weak star topology is also respected by these things. We know it is true for the Fourier transform, so I incorporate this into this setting. And then there is a very good point that I just want to mention, because I think it's not written down in these slides, is that what happens if you take the dual of a Banach space with the weak star topology. So you're looking at all the weak star continuous linear functionals on the dual space. What do you get? What do you get here? You're getting the original space back. So in that sense, I'm not using Hilbert spaces. I'm not even making an assumption about reflexivity, but by adding this extra property, I'm getting it for free. So in this way, actually in the book of Conway, you find a very nice proof. I thought it's very complicated. I was looking up the proof. Is not so complicated. What you need in the proof is, if somebody is giving you a weak star continuous linear functional, then of course there are neighborhoods. You have some epsilon delta condition or so. And then the main trick is, if something is 0, you can rescale it arbitrarily much, then it's still 0. So in this way, it's boiling down to the question, if somebody tells you here's an abstract functional which has a null space, so the hyperplane generated by that functional is containing the intersection of the hyperplanes coming from a finite set of linear functionals, then it must be a linear combination. And if you think of this in linear algebra terms, it just says, well, if you have a bunch of lines and they are linear dependent, so they are having a common line, if you have something sitting in that line, then you can, of course, do linear combination. So you're doing linear algebra, more or less, to find out that this functional is a linear combination. So somehow, the definition of the weak star topology clearly uses elements from B, and by this simple analytic trick you get, it must be a linear combination of this You're not realizing that you're working with an infinite dimensional space. You don't have to do topology or so. Just use the definition of weak star convergence. And so I think it's quite useful to have this knowledge. Okay, so then the next thing is to tell you that actually in the literature you find a lot of Banach-Gelfand triples. What is, if we talk Fourier analysis, your favorite Hilbert space? I guess you would like to take L2 of the torus. That's really where Fourier analysis and functional analysis starts. Now, could you imagine what kind of Banach-Gelfand triple you would have? Yeah, and the Fourier transform gives you coefficients. It's the Fourier transform. Now, either you think you can have some spaces here, you can make spaces here. So what could be a nice Banach-Gelfand triple? Sequence spaces around L2 such that one is a small guy and the other is a big guy. I guess it's not, if you think a little more, if you have more time, I don't want to. L1, L2, L infinity should be the prototypical Banach-Gelfand triple because clearly L1 is inside L2, the dual space is containing these things. Small exercise, what is the weak star topology on L infinity? Instead of uniform convergence, you have pointwise convergence. Because for every unit vector, and therefore for every linear combination and so on, for every L1 function, you have convergence. So, are the unit vectors or are these spaces dense in L infinity? Answer no, because what you reach are the zero functions, the functions vanishing at infinity. Are they dense in the weak star sense? Yes, of course. Look at constant 1. I take 1, 1, 1, 1, more and more. Every coordinate would say, here, as soon as you have put a 1 here, you can add more 1s and it's convergence. So the good thing is you have also here already the advantage of density. So if you know an operator which is weak star dense on the small space, you can expect to know it on the whole space. Okay, now, what are the functions which have Fourier coefficients which are in 1? This is just A of t. And so the Venus algebra of absolutely convergent Fourier series. And I think, why did he introduce it? Because there are all these troubles with pointwise convergence of Fourier series, and he tried to avoid it. And then people were doing functional analysis. They were looking at the dual space. They called it the pseudo measures. Why? Because ordinary measures are, of course, linear functionals, but there are some more, so a little bit. But if you look from modern point of view, it's, of course, the Fourier transform, the classical Fourier transform, establish a Banach-Gelfand, I call it even a unitary Banach-Gelfand triple because at the Hilbert space level it's unitary, a unitary Banach-Gelfand triple from this triple A of t, L of pseudo measures to the prototypical example. And you see more and more of these things. So now I will try to tell you how to, so I have already told you yeah, maybe one thing which I do on the blackboard and then I try to do mostly the slides is, for me a pedagogical model is, which I also do now more or less all the time, is to say, think of the number systems. So in the same way as the objects here are having increasing generality and increasing difficulty, I'm telling you, think of rational, real, and complex numbers. Why are complex numbers interesting, let's say in the context of Fourier analysis? Because the exponential law is much simpler than the addition theorems for cosine and sine and such things. So you have more freedom, we can do things with generalized distributions, or we run into generalized distribution, compute, convolve them, and suddenly at the end we have ordinary functions. Why would we use R? Well, because it's complete, whereas this is not complete. This is not a good analogy because each of them is complete. It's more Q. I would sell you Q as a space where certain things are easy. And here you have more objects that can be used. So what is easy in the rational numbers? What is the inverse of 5 over 6? 6 over 5. You just turn it around. What is the Fourier transform if you apply it to an L1 function. Oh, is it integrable? We have to fiddle around. If you have a test function, you say, okay, the Fourier transform is a test function again. It's integrable. I apply the inverse Fourier transform. So Fourier, I would take that analogy. Here, inversion in the sense of numbers is easy. In the case of test function, applying the transform that you have, many other Banach Gelfand Triple morphisms are of the same way. You can do things in the way you would like to do them. There's actually another aspect that I like to bring in. All these things can be done on general locally compact abelian groups. And as I keep emphasizing, because I also like to do MATLAB experiments, is if you can do it for general groups, you can also do it for finite groups. So when I do my MATLAB experiments, I work on the finite group. So what are these operators then? I mean, then of course everything is collapsing. It's just C to the power n, and n is the order of the group. But what are operators? Operators are matrices. When I tell you something can be done with matrices, and then you go to the continuous domain, engineers would say we go from discrete variables to continuous variables. Well, instead of a matrix, you go to a kernel. A kj is going to capital K of x and y or so. And a matrix multiplication goes to integral operator, writing the integral. Yeah, so maybe an operator, integral operator, tk of f at x is the continuous analog of a matrix multiplication or so. These are continuous rows and columns and so on. If you transfer these ideas from linear algebra to function spaces, it turns out for the function spaces, for the small guys, everything can be taken literally. And the second question is, how do you prove the Plaucherel theorem? Well, you're working on the safe ground and then extend it by abstract arguments. So you verify it's isometric and then you do it. And so it's the same here. I mean, usually you say something like, think a little bit more carefully about the complexity of 1 over pi squared. Or how do you compute? Nobody has any doubts it exists. But when I ask you to compute it, what would you do? You would try to approximate it with rational numbers. Actually, you would have pi with a certain length. You would multiply pi, then take the inverse, and so on. Well, that's exactly what we do here. When we do the Fourier inversion of some bad guy, we make it nice, we pull it over, and so on. So that's really the strategy that one should follow. Now, the concrete thing is the function space is 0, and it comes through time-frequency analysis. And the key players in time-frequency analysis are time shift, frequency shifts, they commute, and especially the short-time Fourier transform. The short-time Fourier transform is correlating, the f is the signal that we want to analyze, and we correlate it against typically a Gauss function or a Schwarz function that is moved around in time-frequency plane. Yeah, I put down here a link or hint. If you Google for STX and ARI, you can download the software which Peter Balach offers from his group, the Acoustic Research Institute. And then you would have a real-time version of such a spectrogram. This is a piece of Beethoven sonata, and that is a function of two variables, where at each moment in time you see the frequency distribution. So the spectrogram is such a thing. And now I think I can skip some other parts. The important property is if you choose a window which is normalized, so maybe you read the first equation with window G equals G1 equals G2, and assume that it's normalized, and you see that the scalar product of the spectrograms is the same as the scalar product of the functions. So you are having a mapping. Usually I'm thinking of this. This is our signal space. I'm mapping in the bigger Hilbert space of more variables, and there is a closed subspace, but it's isometric. I mean, all the angles, all the energy is preserved, and therefore the inverse theorem is allowing you. I mean, whenever you have a matrix which is embedding Rk into a higher dimensional Rn, then the adjoint matrix is the inverse on the domain. So you can just write that down. And because everything is continuous, you're seeing that the function up to some normalizing factor is a superposition now of this. And here you can even choose the window. So think of gamma equals G, and then everything is fine. Now, if you compare this with the Fourier transform, or Fourier inversion theorem, then the Fourier inversion theorem says you get this by doing Fourier synthesis. Fourier synthesis, these chi-s are the pure frequencies. Chi-s of x is e to the 2 pi I xs, maybe with a scalar product. And that's actually, well, a scalar product between the function f and the character. Because these characters are bad guys, they're not in L2, you have to be careful. The f has to pay a price. But somehow the idea is it's like a continuous orthonormal system, or people doing now continuous frames, I would say it's a continuous tight frame or something like this. Now, this is intuitively nice, and we were keep saying for a while, well, you know, the disadvantage here is that the building blocks are not in the Hilbert space. So if you take a Riemannian sum, a finite sum of such terms, it's not even Hilbert space. So how can you say it approaches the function? Of course, it's only in the weak star sense. But if you would look at this thing here, the good thing is that the time frequency shifted versions of this gamma, they are in this space. And then we realized, well, but we have to sit down and prove something, and that works actually. And again, Ferenc Weiss was then doing, I mean, I have a very general, but rather abstract and involved approach to this question, but he was doing it in a classical way. So you can really take this here, and if you choose, let's say, G equals gamma, and from the space as 0. So reasonable things. What engineers would do actually, they would not use the rectangular function, they wouldn't use the sinc function. Then you can take this integral and take just sufficiently long, I mean big square from the spectrogram, and sufficiently fine sums, and you would have an approximation. For every f in L2, it would approximate in the L2 sense. Actually, for every f in S0, it would approximate in the 0 sense, and even if it's in S0 prime, it would be in the weak star approximation sense. Okay. Now let's disclose. We don't have to do all this. For those who have not yet seen the space, the definition of the space using the short-term Fourier transform is quite simple. You are just imposing the L1 condition. So what do you know about the spectrogram for a general L2 function? The L2 norm of the function is the L2 norm of the spectrogram, so it's in L2. Cauchy-Schwarz says I have taken scalar product, so how big? What is the sup norm? Well, at most the size of the f times the size of g, but it's normalized, so it's the size of f. So it's a bounded L2 function. Well, but the bounded L2 function does not have to be in L1. It may decay slowly, but only by squaring it is integrable. But so this is really not very strong, but a mild extra condition. Now, it excludes all the functions which are not integrable. It excludes all the functions which are having a Fourier transform which is not integrable, which is not integrable. Therefore, it excludes all discontinuous functions. But every piecewise linear function, for example, is in this space. So a triangular function, of course, is compactly supported in the Fourier algebra. All these functions are in the space, and the absolutely convergent sums are in the space, and so on. So it's a lot of sufficient conditions. And if you ask what happens with the spectrogram as you do the Fourier transform, the best thing is you think of rotating by 90 degrees. So because if you choose the Gauss function as a window, which is a very good choice, then you have that the spectrogram of f hat of the Fourier transform in the classical sense is just the absolute value. It's just the rotated version. And everybody sees that rotation doesn't change the L1 norm of a function of two variables. And yeah, it's the minimal space. And the short argument would minimal space about among all the spaces where the time frequency shift is constant. I mean, is norm preserving. So if you give me an LP space, I would say, okay, it's translation invariant. If you multiply with a character with a pure frequency, the absolute value doesn't change. So LP spaces are obviously containing the S0 space, and by duality are contained in the dual space. So they're all between the small guy and the big guy. So what is the argument? I use this representation in the normalized form. I put norms to the inside. I use that this is constant, pull it out, and the rest is just integral, which is the definition of the L1 norm. So it's just a very simple proof why it's minimal, and this minimality makes it quite useful. Yeah, and just kind of a quick list of properties that we have. It's Fourier invariant, so even for general groups, it's going to the right group. If you integrate along a subgroup, so in the plane, you integrate along the y-axis, you get functions on the x-axis. Of course, they are. If you restrict to any subgroup, it's fine. And the most important property maybe is the so-called tensor product property. So, if you are giving me a function of on R2 in that space, so it's a direct definition, I can guarantee that you can split it into functions of variables, of individual variables. Of course, it's not a finite sum. One can prove that it's not possible to write everything as a finite sum, but absolutely convergent sums. So you write function fn of this form, gn of this form. You take the norm of this in S0 of one variable, of this in one variable. You sum up, and it's finite. And even the total sum is comparable, and so is the projective tensor product norm. Why is this so relevant? Because if you're, maybe I'm skipping this, because essentially I'm getting a kernel theorem from this, and maybe because time is running short, I should just go on. Yeah, so some people say almost all my talks contain this slide, which is true. This is the typical situation that you have when you plug to the, this is so to say the full plot of all the function spaces that are relevant for normal discussions. So the Schwartz space is small but complicated. It's indicated by this family of seminorms. The nice space is the L2 space, which is the red circle here. If I reflect this object along this circle, you get the temper distributions. Interesting question how to do these plots in MATLAB. But, these are trigonometric polynomials, by the way. Now, I use L1 for this symbol, so there are L1 functions, not in L2 or so. But if you rotate L1 by 90 degrees, you get the yellow object, which is a little bit hard to see because it's hard to recognize whether the function is in the Fourier algebra or not. But it's inside C0, which is this square here. So somehow, as you see, there is a very nice circle, which is a zero space, and there is another outer circle. And this location tells you exactly how the spaces are. So the big space is inside the temper distributions, of course, and so on. Now, how do you define the Fourier transform? Of course, by duality. Yes, the last theorem is something like this. If somebody tells you that the distribution is 0 prime is concentrated on a line, then you think maybe there's a distribution living on the line, so coming from one dimension, and that this is also valid, so kind of you can do this. Yeah, in particular, if somebody tells you here's a distribution in a 0 prime which is living on a lattice, so on a discrete set, then, and that was a point where I had discussions with Werner Kotzek when we wrote our article on Gabbar Analysis. He said, well, come on, why do you want to use a 0 prime? It's your favorite space, okay, but people know Schwartz space. But then there was a point where we were saying, well, we have some operators, the spreading function, whatever it is a distribution as 0 prime, and it's supported on a discrete set. So assume you know that there's a temper distribution concentrated on a point. Let's say on the real line on the point set. What is it? Well, it's the sum of Dirac and derivatives. So it can be a Dirac prime, anyone. At different places it can be different. In this space, the test functions are locally like the Fourier algebra. The Fourier algebra is not having really any smoothness. I mean, it's continuous. It's a little bit more than continuous, but it allows you to prove that if a distribution in that space is concentrated on a point, it's a Dirac. And that's then kind of one of the arguments where you say you're in a smaller space, so you have more information because you can do certain things. maybe let's see what else. Yeah, another point which I like to emphasize is Poisson's formula is extremely important. I really take the classical version saying that if you have a subgroup, can be the integer lattice on the real line, and you take the function, sum up the values over the lattice, then it's the same as the Fourier transform along the orthogonal lattice. How do you prove it? Very natural proof is take the function, periodize it. Then you have a periodic function. The periodic function has Fourier coefficients. The exponential law tells you that you can compute very easily that the Fourier coefficients of these periodized functions are just the samples of the Fourier transform of the continuous function that you start with. Okay, then you say, okay, so this new periodic function is the sum of its Fourier coefficients, and you write it down. And then you have the trouble almost everywhere, and this is at point 0. And nasty people make up pathological examples, so even with some slight decay on time and frequency, that say, well, Poisson's formula is not always valid, which means it can happen that you fabricate a function which is converged, where both sides are convergent, but it's not the same, because exactly at that one point the representation is not valid, and that's not a contradiction with the classical viewpoint. However, if the periodized function would be in A of t, everything would be fine. Well, if you start with a function in the Fourier algebra, you periodize, then one of the theorems is saying, well, I'm living in the S0 of the torus, and the 0 of the torus is just, it's the Fourier algebra, but local equals global, because I'm on a compact group, or on the Fourier transform side, I've restricted the S0 space to a discrete subgroup. What is S0 of a discrete subgroup? It's just L1. So I have, in both cases, I have an argument why for S0 functions this is really valid, and that's what engineers really use. They want to know that if I have a function, please take it in S0, and you periodize it the same as sampling the Fourier transform, or Shannon sampling theorem. If you sample it on the time side, it means replicating on the Fourier transform side. So the Shah distribution is, as part of this argument, is a linear functional on S0. So it's clearly an unbounded measure, but it's still a linear functional on this thing. And therefore, you can take its Fourier transform. So we all know that this version of Poisson is an equivalent statement that the Shah distribution, the sum of the Diracs of the discrete co-compact subgroup, is going into the Shah distribution of the orthogonal subgroup. I think I should come to an end by just at least mentioning that I'm currently investigating all the weak and soft statements that people are doing in engineering books to see how to describe them in a weak star using the weak star convergence. For example, how do you motivate the Fourier transform? You're saying, well, I have a function which is decaying, and then they draw a function with compact support. And if you make a periodic version of it, it has a Fourier series expansion. If you make the period long and long and long, or somehow magically you get some formulas which look like the Fourier transform and the inverse Fourier transform or so. And well, in this case, it's really what happens if I take the Shah distribution, which is a Dirac comp, and if I stretch it, in the weak star sense, it really goes, in this weak star sense of this, it goes to infinity. And so convolving with a Dirac with very long periods is a process which is having a weak star limit. Going to the Fourier transform domain, of course, you all know the Fourier transform of those Dirac measures, well, they're Dirac measures. While I'm stretching on the time domain, I'm compressing them on the frequency domain. But on the other hand, the isolated Dirac at 0 is left alone at the end. I'm stretching my Diracs, and they're moving to infinity. At the end, only the Dirac is remaining. What is the Fourier transform of Dirac? The Fourier transform of Dirac must be 1, because convolving the Dirac at 0 is shifting by 0 is identity. Multiplying on the Fourier transform side by 1. So these Diracs, they're getting closer and closer, and they are convergent to constant 1. Well, in the distributional sense, I should say Riemannian sums are convergent to the Riemann integral. So the Lebesgue measure is the constant 1 taken as distribution. So you integrate constant 1 against f, and you would say it's the integral. And I'm saying, well, but what is the integral? The integral is the limit of Riemannian sums, and Riemannian sums are a denser and denser samples, so they're a linear combination of point measures, but with the right amplitude, and we have to see that the amplitude has to be compensated. And that's what the engineers put under the rug. They just say, we have these Fourier coefficients, and we plot them somehow such that magically we see a uniform folder. No, I'm saying, no, these are discrete measures. Each periodic function has a discrete Fourier transform, and these discrete measures are convergent in the weak star sense to the right limit. Okay, at the very end, I would like to mention what is, probably I don't have to, yeah, maybe I go back to this picture with this spectrogram. How can you characterize a 0 prime, the dual space, via the spectrogram? It's very easy. It's all the tempo distributions which have a bounded spectrogram. So what is norm convergence in the 0? It's uniform convergence in the spectrogram. Well, for which window? Fortunately, it's easy to prove, or a property or consequence of the properties of the 0. Take any window as a 0. It's always the same. So if it converges for one window, non-zero window in a 0, converges for every other window in the 0. Now, weak star convergence must be weaker than norm convergence. What is weaker than uniform convergence for functions which are looking like this and bounded? Pointwise convergence. But if you have pointwise convergence, you have pointwise on finite sets, and by standard argument, uniform convergence over compact sets. And then I'm again sorry for repeating this statement, but I'm saying, well, there is this audio engineer, and he tells me he has a perfect recording, a very high quality recording of a nice piece of music. Then I'm saying, yes, but it's ridiculous. It's just a weak star approximation. You tell us that you have 3 minutes of recording from 0 to 20 kilohertz. So in this infinite phase space, it's just a little tiny rectangle of 3 minutes times 20 kilohertz. But for our ears and for our perception, that's good enough. In the same way as maybe a 1 million or 20 million pixel image is good enough to produce a poster, and we say it's the image. So having these kind of interpretations in my mind, I'm feeling much more comfortable about the role of weak star convergence. It's really a very natural convergence. It's easy to explain in this context, and it's to reality of what we really do in all these things. So it allows, with the weak star convergence, you can really give a more solid ground to many of the things that people in engineering would do with hand waving and say, somehow we approximate, and then you ask, well, in which sense? And say, well, we cannot make it precise. Or that's where I'm coming back to my statement, where choosing the right function spaces and the right way of convergence may help to give solid mathematical statements. Okay, I think I'm already much over time, and thank you very much for your attention. Motivation.
Overview, by the way, so S0 is also called Feichtinger algebra. So are there questions? It's possible to see once again the legal definition.
Yeah, so it is the integrability of the short time Fourier transform. Here, yeah. So the earlier result is the fact that more or less as a consequence of Plancherel or so, if you have a window which has norm 1 for simplicity, that's always assumed, then the L2 norm of the function and the L2 norm of the spectrogram is the same. So we're talking about functions which for simple reasons, I mean for this non-trivial reason based on Plancherel plus Cauchy-Schwarz is a bounded, continuous and square integrable function. But that may mean that it's just decaying very slowly, but not good enough to be integrable. Only by squaring it, it becomes integrable. And if you say, well, the ones which are not integrable themselves, thrown out from L2. So I'm staying within L2 and take all the functions where this expression is finite. I verify that it's a norm, that it gives you a Banach space and has all these properties. And there is actually I mean, the question is, this depends evidently on on G. So the abstract claim is, if you have other ways of defining the space, then one can show that every element from the space can be used as a window, and you always get the same space and equivalent norms. So for a while it was really the question, which one should one use? And I mean, we have discussion, Mats and I. In the general group, there is no canonical window, but on the real line and Euclidean spaces, it's very reasonable to choose the Gauss function, a normalized Fourier invariant Gauss function. That's probably the best choice for defining the space, because then some properties are coming out for free. Is the short-time Fourier transform? That's where, so to say, I was showing you this picture. It's this guy here. So essentially, it's trying to identify the energy within the time frequency plane. So you think of a musical score, and so at this moment I play some accord, and at this moment I see some accord, and so if here I would say, what is the reading of this? That at this moment in time, so sample number 600, which I have to say is at this moment of the recording, I see that the here and here and here and here are some strong components. So if I take that cross section, it would be the frequency profile, and essentially you think it's also called a sliding window Fourier transform. So you cut out from the Fourier transform a window, and you analyze the part here. And everybody understands that if you take a window which is too short, you cannot do frequency analysis by the uncertainty. If somebody is giving you 10 samples, what meaning of frequency analysis do you have? If somebody is saying, well, but then take long windows, extremely long windows with full Fourier transform. The full Fourier transform tells you maybe there's a lot of C and G in the piece, but it doesn't tell you what melody has been played. So if there are already too many changes within one window size, it's not good. In this program, you really can play around and can say it should be 50 milliseconds or 200 milliseconds, and then you see it's really very nice. It's getting more smeared in frequency if the window is very short, and it's getting more smeared in the other direction if it's very, very long. Because if a long window is, there occur changes within the window. That's not good. But if you want to have a high resolution of a pure tone to very adjacent frequencies, then you have to wait long enough to differentiate this. I mean, that's very plausible actually then. And then, sorry, and just to mention, the short-time Fourier transform is the analog of the continuous wavelet transform, if you're familiar with the wavelet transform. So from our point of view, that's another direction. You could say whenever you have a group acting on the signals, here it's time shift, frequency shift, and the third variable can be ignored. It's the torus with phase factors. Or the wavelet transform, you take the function, you move them around, and you dilate them. Then you can produce a function on the group level by just saying this pi here. For fixed, you fix a pair of elements in the Hilbert space, you let the group act on one of them and see how it changes. And somehow the idea is that typically this will move around things in the whole group, and in the wavelet domain it's the upper half plane or the right half plane, depending on your viewpoint. Here in our case it's the time frequency plane. So I'm asking at which time and which frequency do we have a lot of energy? In that sense it's really very close to a musical score.
Okay, so
I'm around for a while, yeah. Thank you.